Hi, today's video is a bit special. I will have a guest, Mike Beaumont, and we'll discuss Nonlinear FEA. So I really hope that you will enjoy the show. The only thing is that I've messed up during the recording, so you will see me looking as if I'm using a potato as a camera. I really apologize for that. It was a technical mistake that I cannot fix right now, so I hope that you will forgive me for that. The quality of my part of the video gets better later on, but it will be abysmal anyway. The good thing is, though, that we don't use any visual aids, so you can treat this as a podcast. And this actually got me thinking that there's surprisingly little podcasts about engineering, calculations, design, and so on. So if you would be interested in such a thing that you don't necessarily have to watch, you can just listen, let me know in the comments. I'm really interested in that because I was thinking about doing a podcast and I never started. So maybe this stupid mistake with the video that makes the video unwatchable in some sense, but good to listen, will actually be the first step for doing that. So if you'd be interested in podcast done by me about engineering and FEA, definitely let me know in the comments. And in the meantime, please do enjoy the episode about nonlinear FEA. I really hope that you'll have a lot of fun. Before we start, Mike, could you tell us a bit about yourself? That would be great.
Yeah, Lucas and everyone. So I'm a structural engineer working in the resources sector in Western Australia. Most of the work I do is designing plated steelwork, mostly for handling bulk materials. That's probably the main thing that keeps me busy during the day. And obviously, as part of that, it's not something that you can just use standard closed form equations. So that lends itself well to FEA, really. So I started out like probably most people did with FEA, coming out of uni, not really knowing anything about FEA or having done the very basic course, which doesn't tell you how to analyze and design. It doesn't tell you how to design anything or to understand results. So you kind of just fumble about in the dark. And it's probably maybe 4 or 5 years ago, I found Lucas's blog, and it really set me on the right track of really just knowing what I didn't know and what I needed to know. That's probably the hardest part, is actually knowing what it is that you need to learn with this sort of stuff. So it's been an interesting journey, I think.
Yeah, it's like the unknown unknowns is the biggest factor that plays it all, and you're not even aware, right? That's always a fascinating thing. So to set the stage about like how to convince people, if this makes sense, but also just to discuss nonlinear FEA, I think that it would be good to start with the benefits. Like obviously, nonlinear FEA has its issues, and we'll definitely talk about those later on. But to keep the show positive, let's start with like what would be the benefits of nonlinear FEA. Like I'm sure that it helps you in your work, but I'm pretty sure that folks would like to hear what you think about it, and I will drop my 2 cents as well, I think.
So if we're talking about the benefits of nonlinear FEA compared with linear FEA, I guess we're looking at.
Yeah, actually, I would say there are many ways in which you can do design, right? You can do the closed form equations or just hope. You can just wing it. Or do tests of everything. So like I wouldn't necessarily compare nonlinear FEA to only linear FEA because there are other options too, but in general, like the linear FEA seems to be the closest competitor.
Yeah, when we're talking about closed form equations, you're very limited in the application that you can apply them to. So of course, things like beams, which, the code covers, really well, comprehensively, these can all be covered by closed form equation. You'd be wasting your time, doing a beam structure with nonlinear FEA. I think anyway. So it certainly has a place where it's applicable. So really, the competition for nonlinear FEA is linear FEA, I guess. And the main issue, I think, with linear analysis is that, and I think you've mentioned this a few times in your posts, is that really you're guessing the whole time in every stage of the analysis, really, because you're relying on basically you have to sort of decide what you can ignore, and unless you're really experienced with that exact structural form or that exact detail, it's going to be pretty difficult to know when you can ignore a stress concentration, or whether a linear buckling factor is reasonable, or if you can accept a LBA factor of 2, or if it needs to be 10. So in this regard, doing a full geometrically and materially nonlinear analysis with imperfections, it takes a lot of the guesswork out of it. There's a lot less, I guess, messing around with the results and post-processing, I think.
Yeah, like I always remember one of my friends of mine, Sondra, told me once that they do nonlinear FEA even though it takes more time, mostly because even though they took more time to do the analysis, they spend less time convincing the customer that the outcomes they receive actually make sense, because like you can actually prove stuff. And like I'm sure since you do design just as I do, even though we work in slightly different industries, you most likely had those discussions where people say like, okay, we've got this linear outcome, maybe you deliver it, maybe someone else did, and like, why did you assume this or that, right? Like, how do you know that it's okay? And there are no, like, you cannot prove that in any meaningful way. You just can have something like, my authority say that when I do this, I can ignore this much and I will go that route, right? But nonlinear FEA actually gives you the tools to show that you know what you're doing, basically. Right?
Yeah, and also the fact that it gives you, the engineer, confidence in your own designs when you can benchmark outcomes that you're getting against simple cases, like comparing a column buckling against what the code would predict for an axial load. It should come out pretty well spot on with a nonlinear FEA, but attempting the same thing with linear FEA, it could be up by a factor of 10 from LBA.
yeah.
So
that's true. But
when you're struggling to benchmark simple cases, it's hard to have confidence in your own design. And at the end of the day, you're the person who's putting your name on this stuff. You want to be doing that with as much confidence as you can, I think.
Oh yeah, that's definitely true. Although I think that there is one point about confidence that always like scares me, or at least makes me uneasy, and that is that I know a lot of people, or at least I've met a lot of people who are absolutely confident in their linear FEA design, because like it's like the Dunning-Kruger effect in some extent, right? Like as long as it works, it works, and if it works for 10 years, no matter what you do, you're dead certain that it works okay, right? Like I'm sure you've encountered people like they see your nonlinear design and it says that it's like different than what they did for the past 20 years, right? And they tell you, you're dead wrong. Like we've been doing this for 20 years and it must be as we've done because nothing ever happened. Right? So I guess that part of confidence, it's funny. Although when you're aware of what is going on, then absolutely nonlinear FEA would give you awareness. It's just the problem of like, you have to be aware. And sometimes the awareness of it is difficult, I guess. But so nonlinear FEA can give you a lot of confidence in what you do, right? But it's not for free, I would say. Like, what would be the main disadvantages that you will see in doing this kind of analysis in your work, like from day to day, right?
So I guess the biggest disadvantage would be, and it's really probably the only disadvantage, the amount of time it takes just to get a solution. So like, a linear analysis with a few 100,000 elements might take a few minutes to solve, maybe 5 minutes to solve a linear static analysis, whereas to solve, however many increments you need of a nonlinear solution, yeah, you might just leave it running overnight and come back in the morning.
Yeah. Just to learn that you forget to implement self-wait, which is classic, by the way.
Yes, every time. Every time there's something stupid like that, and you go, damn it, I've got to rerun it again. So the amount of time it takes to get a solution out is definitely there, but I think it's worth it though to be able to, like, if you manage your time well enough, and you can set things going so that they'll be ready for you when you need them, then it's not too much of a problem. Yeah.
It requires organizational skills too, right? You have to think through what I need to do today to be able to put the analysis to run during the night, and what we need to do this week, so the most of the calculations are done over weekend, right? So obviously, the increased planning is needed. And then if a customer calls you on Monday and say, hey, we need to move this somewhere, or add additional load, and you just spent 40 or 50 computing hours on something, that's very sad news. So I guess that changes are also a problem in nonlinear FEA. It's not easy to redo something, right?
I suppose also communicating results to colleagues and to customers may just be used to going, oh, why is that stress greater than yield? That can't be allowed. But it often is completely acceptable to have components yielding. Well, usually it's allowed. Like if you think about plastic section modulus in a beam, the entire thing is yielding. But
yeah, exactly.
It's often,
and nobody talks about it, right?
No, but it's often people get quite alarmed when they go, wow, that's such a big yield zone. But then you have to sort of calm them down and say, no, it's okay, and this is the characteristic resistance, and it all gets knocked down, and there's load factors, and so
I actually have a GIF of beam that bends with plastic section modulus to show how much yielding happens to customers, just in case. It's handy waiting on my laptop every time I talk with someone.
Yes, there's quite a lot of reassurance needed, I think, to people who are seeing this for the first time.
Well, for better or worse, engineers tend to be pretty conservative people, right? It comes with a job. All new ideas are great, but nonlinear FEA definitely is something that we start using relatively recently. If you consider the time span from Egyptian pyramids done by the first engineers to today, it's only a fraction of a second that we use nonlinear FEA. So it will take some time to get used to, right? I wonder if you would hit the software. It depends from country to country, but I remember that to buy the first real nonlinear FEA solver, we had to save money for a year in my first company to be able to afford the license, right? So obviously it depends whether you work in a big company or start your own company, which country you're in, and so on. But I always feel
I think there's a lot more affordable. I think there's a lot more affordable options out there now, though. The software that we use is relatively cheap compared to things like ANSYS and stuff like that, and the nonlinear solvers come with the base package. So
there are even open source things nowadays, right? They aren't as easy to use, I think, although I heard many good things about some of them. So obviously, it's when I was starting out, somehow I never thought about searching for the open source software. I just assumed that I will have to buy one, and I did the best market research I could, so I just Googled it, this is how we started. But that's true. It doesn't have to be such a big drawback as it was at least a decade or 2 decades ago, right?
I think actually another problem, I guess, and it's not really with nonlinear FEA itself, but it's the fact that it's very difficult to get started. Just when you're learning it, there's very few good resources out there, really, that actually point you in the direction of, in simplistic language anyway, like the Eurocodes are good. So there's a lot of information in them, but man, you've got to work hard to figure out what it is they're actually trying to tell you to do.
I must confess that there was time in my career at the very, very beginning that I would try to convince you that Eurocodes were written by people in a conspiracy. And the conspiracy was to describe it so badly that you have no chance to do that so they can get all the good job out there.
I'd believe you as well. Like, you read it and you go, okay, what the hell is it I'm actually supposed to be doing with this?
yeah, it's like the first, like I was even like considering writing like a scientific article about the conspiracy at some level, but luckily the thesis tutor told me like, Lukasz, like, please don't, like, I beg you don't. so I never went there, but yeah, it was super cool. Yeah, starting is tough. Like I just basically like press every button in Abacus when I was doing my PhD, and it took me like a year to converge first analysis. So only the fact that I just had to finish my PhD forced me to learn it. Like otherwise, like I'm always like shocked that you found this in you to like pursue this without the pressure of university, like forcing you to go this route, you know? Because there are not many people who I know that use like efficiently nonlinear FEA, and they haven't learned it from like PhD studies. Because, you know, PhD is like a wonderful place. Someone comes to you and says, you have to do it. And ta-da, now you have to do it.
I kind of got thrust into it, I suppose. In the role I was doing a few years ago, I had an opportunity to basically, you know, just do FEA. And I thought, okay, it looks really interesting. But if I'm going to do it, I might as well do it right, I guess. I don't know, like, it would feel a bit strange to do things and go, I'm not really sure about any of these results. Yeah, I'm getting pretty pictures, but I'm not really sure about them. So, yeah.
Well, yeah. From there, you basically have like two choices, right? You can either do what many people do, which is, the pretty pictures look pretty, and we kind of know that it will be kind of okay, so I will accept them. And like, you know, after 20 years, you're absolutely certain that your criteria of accepting the pictures is okay. Or you can like dig deeper, but it's a surprisingly deep dig to dig enough to know what you're doing. That's the problem for sure. Yeah, so would you consider the effort of going there worth it? I mean, like, I didn't have much choice. Like, the thesis tutor told me, Łukasz, this is a PhD. You're doing a nonlinear FEA of this shell, whether you like it or not. Right? So I kind of can say I learned FEA to make a PhD. Right? So like I had like at least there was something forcing me to do it, right? But your story is obviously completely different there. Would you consider worth it? Like, you spend a lot of time, energy in learning it, right? And it wasn't easy, absolutely. I'm sure of it. So would you like recommend it? Or would you say like, it depends on what you do and stuff like that?
It probably depends a lot on what your expectations are and what your roles are. So if you're someone who's primarily designing beam structures with standard connections and things that can be easily covered by the code, I wouldn't think there'd be much use to it. But if you're routinely dealing with, you know, exotic things that aren't necessarily covered by standards, then yeah, definitely. It can be a lot more interesting doing these kind of structures, I find. Like when we're just doing beam structures, which can be automatically calculated by the software and all the beam size and connections designed, it becomes a bit routine. I think it's a lot more hands-on, I think, doing it this way, and you feel like you're understanding a lot more about how things are failing and what causes failure to happen. And I think it's very valuable to see exactly how a particular structure will collapse Oh, we'll probably class.
We're not as pessimistic. Yeah, like the thing that I would add there, and I wonder if you agree. Like I realized this quite late after learning Nonlinear FEA, that thanks to the fact that I've learned how Nonlinear FEA works, I actually start understanding more things. Like when I design beam structures, like I've been an academic tutor for like a decade. So I taught a lot of courses on structural steel design. And initially to me, that was like, punch the numbers into equations, check this, check that, whatever. And then, you've got the outcome. And like as I learned how the nonlinearities work in real life, I could assign meaning to those equations to some degree. I think that I understood more. I'm not sure if this is needed, though. Like, it doesn't change the equation itself. Like the outcome will be the same regardless if you understand what you're doing or not, although it's always better to understand things, right? But while I agree that it's not necessarily useful in a sense that when you do beam structures and you learn Nonlinear FEA, you'll be able to apply this somehow to the projects. Like most likely you won't, unless you have like a very funky connections and things like that. But I think that the understanding, maybe not necessarily connected with Nonlinear FEA, but understanding of the deeper level of engineering actually makes your work more bearable. Like it's not so boring anymore because you kind of like understand this. Would you like find this in you too, or like, is it my thing?
No, I think it's the same. So, when you're starting out, you're following the code procedure for calculations on beams, and you're going, do this, then this, then this, and this, and you don't necessarily need to actually engage too much critical thinking. I think as long as you're following the procedure in the code, you go, oh, I don't know what slenderness is, but this is how you calculate it.
Yeah, exactly. Like.
So I think being forced to actually engage with these topics, it does sort of give you a bit of a deeper understanding of these things that are in the code, I think.
Mm-hmm.
Which, like you say, they're not going to make you better at pressing the button on your beam software, but
well. Actually, I would say that to some extent, knowing too much may make you work slower. Because like I've been in a situation where people from different companies wanted to hire me to do the training for them. And they say the goal of the training is to speed up the design process. And I said, look, I can help you optimize stuff, tell you like the rough guidelines of things and so on. But if there are things you are missing in design right now, and I tell you how to do those things, like this will make the design last longer, like regardless. Like, so it's not necessarily making it faster, it's making it more accurate, which sometimes may even lead to heavier structures. Because if you ignore the problem for so long, and suddenly you learn, oh, there is something we have to take into account, and it changes the outcome. It can be that the design is better and the structure is heavier. And that's something that can really surprise people. That it's not like all sunshine and rainbows.
Yeah, definitely. But yeah, getting back to if it's worth it to learn it, I think if you are going to be dealing with non-standard sort of things like plated steel and shells like you do, I don't see any other reasonable options, to be honest with you. I know that people live with other options, but
yeah, like so many actually. Like I've received many reports from various companies, like to check it, to verify it as a input to my design and stuff like that. And like you would be surprised how often people use linear FEA to design like plated structures. I would say it's like common, but even in shell structures, like highly nonlinear by definition, practically. They still do like linear butting, hoping for the best, right? So yeah, I would say that it's actually like doing the linear FEA, while may not be ideal, it's actually a reality for like a lot of people doing FEA at work, I think.
So I think there's a lot of self-satisfaction involved with it as well. Like, how satisfied do you want to be with your own work?
Yeah, FEA wizardry. I mean, come on. Like.
That's it.
you know where to punch like yield stress in like limit yield stress in your material model, so you're an expert. Like, you know, Mike, the funny part is that it never ends. Like, I caught myself in it like few times already, that at some level you think, oh, I won't learn anything new. I already kind of know, like, you know, I know how to do Nonlinear FEA. I did it for a few years. So like you think that you don't develop in this kind of work. And then you open your report from like 3 years ago. A professional tip: never, and I mean never, check your old designs. Like, it's unhealthy. It's like, it's not a good idea. But you open it because you didn't know the advice, and you look like, whoa, how could I have done it this way, right? Like, you've changed so much how you do things a long time. So I think that there is a capacity to always be learning. And I think that when you do like basic design, it's actually the capacity of be more and more accurate guesser of outcomes, which is kind of different in the vibe. Yeah, I totally get the satisfaction part, which is cool. So obviously it seems that we enjoy our work. Like, and like, how would you approach convincing someone that it actually works? I know that you have few successes recently, and I'm always happy to do that. Like, I'm willing to share my stories as well. But I think that if we would run a poll, and by the way, I need to do it one day. Like, I would say that like there is a big chance that most of the viewers interested in FEA do linear FEA for a living, right? So there's either a boss or a customer who would have to be convinced that doing things in a nonlinear way actually makes sense. Because the problem is that when you say, let's do nonlinear FEA, you're upsetting the system that was in place, usually for quite some time, right? So it requires a certain shift in thinking and challenging the things that were established many years ago. So, like, how would you approach this? And what are your tricks in doing that?
So, I think when people are seeing this stuff for the first time, they're not expecting to see charts instead of
yes, definitely. Where are the pictures, dog?
Like, really, I could do a whole report without putting any pictures in. Charts are all that's important.
That's true.
So,
I actually always put pictures in, and I usually put like picture on the design load and maximum load from analysis, just so there are nice pictures in the report, because people feel better when they are in there.
yeah, I put them in begrudgingly, just to give people something to look at. But
seriously, I do it with a smile. I love how those look. Like, if I would have to name one thing that is an answer, to me, like, chart is the technical answer, but it's a GIF file with animation of failure that is like closest to my heart.
So it takes a little bit of convincing people that the pictures aren't the main output, and because when we're doing nonlinear FEA, we're solving, you know, maybe tens to hundreds of increments of a thing. So there's no like one, you know, stress state of the structure throughout the analysis. So, you know, there's potentially tens to hundreds of pictures that you could be showing them. So the chart is what communicates the outputs of the load deformations. So I think the only way to really convince people that this is the correct way to be going is really, really simple benchmarks, like a column in axial compression benchmarked against whatever code you're using. Like, there's a lot of stuff in the code which is conservative, but columns seem to be pretty, you know, nailed down. There's not too much.
Yeah, it's actually quite easy to laboratory test that as well, right?
There's not too much undue conservatism from the code in, like, you know, just a simple column axial compression. So it's pretty easy to demonstrate that with an appropriate imperfection magnitude and the material models applied, that the output from the FEA will almost match 100% with what the code is predicting.
Okay.
Depending on how you're setting it up a bit, of course. And then you can show them what linear analysis will output and go, well, this is overestimating the buckling capacity by a factor of 10, and I've got this nasty stress concentration at the rigid links at the end of the column. Can I ignore that? Or there's all these unanswerable questions, I think, in the linear analysis. So I think if you're talking with someone who's familiar with the code and like traditional design of beams and things, it should be pretty simple to convince them through benchmarks like this. Another one would be like just plastic yielding of a beam. That's very easy to benchmark because it's just plastic modulus.
And it like the hidden benefit is to show like how big yielding zone you have in the model. Right?
Yeah, exactly. And you go, look how much can be allowed. Yeah. And then there are more complicated things which we discovered recently, like lateral torsional buckling, which are a little bit harder to benchmark.
That's always fun. But like I get a feeling that lateral torsional buckling, while it's satisfying to nail it down, I think that people don't have this like instinctive understanding of it. Like everybody knows that the equation for critical bending moment is complicated. There are like a lot of parameters, and you can like play around with those to like adjust the outcome, so you could like trick them in this particular case, I think. But like I'm fascinated by your work, like by your way of approaching this, because like mine is actually a bit different. If I would like to convince someone, I usually, luckily enough, I usually talk with customers who are like on the technical end, because there's also like, are we talking about like a manager who doesn't do technical design, or are we talking like a technical team leader, let's say, who understand the design in general, right? So when I talk to a technical person, I would show them like 3 slides of the same structure, like with various loads. And I wouldn't tell them the loads, but I would show them the stress state and say like when it failed. And then like, if you have like 5 pictures, like, come on, like there is like 20% chance that you'll get it. Right? so they usually... More or less, but the guy is experienced. Like I would use his piece that I designed for them as an example, so he kind of knows like what's going on. Let's say that he will pick the correct one, and that doesn't like the choice doesn't matter. That's the twist, because I would say why, and this is what trips people over. And there's like because I can ignore this, and so I would just like slightly higher load and say, and why couldn't you ignore that? Right? Just to show that like there is like no obvious limit, because as you said, when you analyze with linear FEA, you just get one outcome. So you kind of look at one picture and say, it's okay, it's not okay. There are no choices. Like you're not selecting between 2 different values. You just have one and you're okay or not. So it's like an equivalent of looking at like a technical drawing and say, yeah, this will be fine. Or no, it won't be. And you're asking, like, with doing this, I'm asking a question of which one is better, or is both are okay? Only this one is okay? Like, how would you, like, and why? How would you justify your call? And this what shows
like,
people
it's like asking them how much stress can be in a concentration for it to still be acceptable.
Exactly. Like, are you willing to ignore 5 times yield as like a stress peak, right? Yes. Okay. 7. Right? And they instantly know where this is going to, right? Because it's like, 5, 10, 20, 50, okay, 30, 22. Like, let's go like to the range until you have to put a number on it. Right?
You could even do this with the same load and just making the mesh smaller in a singularity and saying, is this still acceptable?
Yeah, but that's like, to be fair, that like people tend to react very stressfully to this. Like you like not everybody is like happy to see that the outcomes change for the same load depending on how you do the FEA. That's not like you can upset a lot of people with that, like especially if they are like basic users. Like I was such a user. Like I even have a YouTube video with the like funny mistakes that I did in my career. Like you would caught me off guard with that easily when I was starting. Like I just didn't know. Like I didn't understand it enough to be aware of it, right? But when you force someone to say, what is your rule of accepting it, like an equation, a value, it suddenly like falls apart. And then like when they realize that this is like really based on their gut feeling, you get, like I feel that I get a space to say like, look, there is another way. You don't have to feel this way. Because the funny thing is that once you realize that this is the case, this feeling is never going away. When you learn something, there is no simple way to unlearn it. And like you instantly know that what you do is like iffy. So like I think that benchmarks are great when you talk with like non-technical people, that you can say like, look, this is what the casual code is, like your technical team can tell you that, and this is the outcomes. And what's even better is like when you have like a laboratory test of something and you can model the failure accurately. Like some time ago, NASA did like a huge, like, was it like a jet engine or something? They did like a huge failure mechanism, and folks that did FEA for them were like 3% accurate of the failure mode and failure load. And I was
Yeah,
like,
right.
huh? That's nice. And the thing was like huge. And I was like, spot on. Like that's what I like, right? And like I was lucky enough to do a PhD, so I have some test results that I can show, like analysis that I can show. But like frankly, I don't think I ever got this deep. Usually people are willing to do whatever you tell them after you prove that, look, you're guessing. Like you have colorful pictures full of guesswork, and this won't last. And they are like, okay, like we need to seriously think what to do differently. And to me, that would work.
I think it's very valuable to have written in pretty clear English or Polish definition of what counts as failure, like in your reports.
Yes.
So that you can say, this has failed and this is why it's failed. And people can then, maybe argue about the criteria, but they're not arguing with you guessing things in the results.
Yeah, and like to even build more on this point is, I often ask, like, because I would use codes, because in my experience, people sometimes are very defensive about what they are doing. Like imagine you've been doing a design based on linear FEA for 20 years, and here I come on the shiny white horse to tell you that it's all wrong. Like you've been guessing for 20 years. Right? And like you don't want to hear that. Like you instantly think I'm an idiot, and you will be defensive about your position. I would say like, okay, so let's consider design standards, because funny enough, many things are designed by rule sets. Right? And you say like my favorite is Eurocode, obviously. And so like, could you show me the chapter in Eurocode that allowed you to do this linear design? Like I'm super curious, like based on which like chapter are you doing the calculations, right? Because obviously you show that it's according to the code, so where precisely, right? And this is what trips people over as well. So I guess that my like way of showing people how it works is firstly to show them that what they are doing so far may not necessarily be in according to the rules. It's like a lot of guessing, and then I'm like I can show you better, because they are interested. So I'm starting with shocking them, I guess, which maybe means that I'm a bad person.
And you have the sort of advantage that you can say Eurocode 315 and 316 have got rules that need to be adhered to. We don't actually have any FEA codes here in Australia.
Okay.
So it makes it a bit more difficult to tell people that we need to be complying with these standards or these other standards or whatever. So usually, previously I was using the DNV RP for a while.
Yeah, I was thinking about that, yeah.
Which is good, but it's probably not quite as comprehensive as the Eurocode. So for the last few years, I've been using the Eurocode ones, especially the new Proto Eurocode, the 3114. That's actually quite a valuable one, I think.
Yeah, it is. It's an interesting read, although I still think that there are things missing there. Like, I guess that this will be a very slow process, and like in coming years and maybe decades, we'll kind of like build the rule set of what it means to actually be able to do a decent nonlinear FEA, right? Because like the cool thing that I like, and funny thing is that was like the main source of me thinking that it's a conspiracy. Eurocode actually requires you to do benchmarking, because like when you have the outcome, there's this K GMNEA parameter that you need to know, and it's like the outcomes you were able to get divided by the outcomes that are certainly correct, or like one way or another, right? And like suddenly you're like, how the hell am I going to get the outcomes that are definitely correct, right? And like I was thinking that it's like a scam of some sort. Yeah, so, but like the meaning of this is so important, and I think that I completely missed that when I read the Eurocode. It was like, look, this is a difficult thing. Like, you need to be certain that what you're doing makes sense. So find a solution you're certain of, and calculate it yourself, just so you know that you know how to do it. And the code kind of like forces you to do that. And like, firstly, I was like really objecting against that, and now I'm like, wait, this actually makes sense. Like you really should. So like in the nonlinear course that I'm doing right now, like you get a chance to do the example before you see me doing the example, just so you can read the description, launch the analysis, and it's like, uh-oh. Like, it's better to learn something didn't work on an example in a course than later on in a design, right? Because for better or worse, it's actually possible to make mistakes, right? Like, you can do things wrongly, like not expect something or not taking something into account, and then like this becomes problematic. At least it can be. So I think that part of convincing people is making them aware that it's like actually a complex thing as well. Like I would actually tell my customer, like, look, this is not like press play and celebrate kind of deal. Like it will take time. Like when I say send a proposal to calculation, it says that like the job will take 4 weeks, but if there are convergence problems, it might take 5. And I would literally write something, and they are like, what's convergence problems? Like, you don't have to worry about it, I will fix it. But like there is a chance that the problem will be so complex that calculating it will be very difficult. And it like in those cases, it might take few more days of computing to get to the answer. So that's why I wrote that.
Yeah, that could be another thing to add to the list of potential negatives with FEA, with the nonlinear stuff. It can be very hard to deal with unexpected results or unexpected solver issues.
Yeah, like there are plenty of those, right? Like you run analysis and something stupid happens, and you're like, "Whoa, how we end up?"
I actually had an issue a few weeks ago where I don't know how, but all of my material properties switched to Tresca criterion. I don't know how, but
oh wow!
So they're all solved using Tresca as the yield criterion, and I'm going, this doesn't look right. Why is this failing differently than it should do? And then had to go back and resolve it using von Mises yield criterion.
And then and suddenly you're just like those 2 computing days behind because you have to recalculate everything, right?
Yeah, luckily it wasn't something big, I had to. It's good few hours to recalculate the whole thing again. It's pain to do this.
I had a sticky card on my laptop screen saying freaking self-weight for like months. Because this would be like a complete classic. You're like happy you're launching this, going home, waking up in the morning, and you're like, oh no, not again. There are pitfalls, sure, but I feel that when you manage to truly convince someone that nonlinear FEA makes sense, that there is a benefit of doing that, they will be willing to accept that. Because, if you explain how things work, the opposite is like maybe we roll a dice or, plot few colorful pictures and ask the guy to just guess what the correct answer is, right? So it's not like you have like a huge choice in selecting your tools in reality. But the problem is that many people are simply unaware of the fact. And like make them aware, like with videos like this one, perhaps actually makes sense. So if you're watching us and you happen to have like a customer or a boss who you need to convince, you can direct them to this video or like reach out to me or Mike, and maybe we'll be able to help you out, because I think that it will actually make a better working place for everybody if people will be aware what's the difference between linear and nonlinear FEA. And I think that that's the important part, that many people and customers especially are unaware of like what is possible and why doing things the way that things are usually done may not be the best for them. And like increasing the awareness is important. I'm a nonlinear FEA enthusiast and evangelist, sure, but it doesn't mean that everything has to be done this way. Like, far from it, actually. And if you're doing like simple things like do linear FEA, that's okay. If you're within what you find reasonable, that's great. I will never say it's wrong, but just be aware. And then at some point you may reach to a phase when you're like, okay, now it's time to switch, right? So hopefully many more people will manage to convince customers. And would you say that it's like a good trend or a losing battle at this point in your industry?
It's hard to judge. I find most people just aren't really aware of what the procedure, quote unquote, should be for this sort of stuff. So even sometimes people will be attempting, nonlinear analysis, but they'll use a single increment to solve it, or they won't be plotting charts to see the deformation response. So they might as well be doing linear analysis basically at this point. So I find myself having to explain the same thing a lot, and I don't know if it's necessarily benefiting other people, I guess.
Well, it is in turn. I mean, like if you explain to a customer how this should be done, and the customer will demand it from everybody else, those other people will learn how to do it as well, and this will, advance their game. And in the end, it should be better for everybody. Although the transition period isn't easy. I will fully acknowledge that, but most of us have many years of our careers in front of us, right? So
yes, I suppose this is what forces people to actually. People being forced to learn these things, like, as you say, from a client demanding it, or as you guys in Europe have, the Eurocodes are not normative and required. So technically people not doing it this way, they can be called out and said, well, you've not designed something compliant with the code. So that should be motivation for people in this field, I think.
I do agree, but I will also add that from my perspective, I've been doing nonlinear FEA for a decade now. Like, I started in silo design, and when I first did projects, I had to literally explain my customer what it is, like why there are no equations in reports. Like they were like, wait, what are you doing, dog? And it wasn't easy. I'm not saying it was easy, but in time, the first thing I noticed is that people stopped being surprised. Like maybe 5 years ago, when I started sending nonlinear FEA reports to customers, they were like, oh, this thing, right? So they maybe were not enthusiastic about it, but at least they saw it several times. And I think that what I do, but also many other companies that do nonlinear FEA, I think that in our best interest is, and I do it, and I'm pretty certain others do too, to write down why and how this is compliant with the code. Mention specific chapters, because this equilibrium paths, the charts we talked about, are drawn in Eurocode. You can say, as can be seen on figure this and that in Eurocode, this and that, we analyze this chart in this and this way, obtaining an outcome, and customer can take a look and say holy moly, this is actually in the rules, right? So and then again, few more years passed, and suddenly I cannot honestly say that people start to require it, but they are happy when they get it. They start to understand that this is something better. I'm yet to get a design request where someone says it has to be done with nonlinear FEA according to this and that code. People usually say it has to be done by this and that code. And while technically it would be the same, it's not necessarily the same, because if you don't know the code this well, someone can do linear FEA, just write that it's according to the code. How will you check it if you don't have the skill set, right? It's not the same thing. But I did 2 years ago, someone was verifying my report, and they called me to ask about imperfections in analysis. What imperfections did you choose? Why those? Things like that. And we talked for 10 minutes. And they were, of course, satisfied with my answers, because the guy was basically just checking if I know what I'm doing. Right? But he did ask about that. And I was like, yeah, it's starting. slowly, but like there is a momentum, and like hopefully it will like grow and move on. But it's still fresh. Like I would say that it's like still an undiscovered frontier, and more often than not, people don't ask me about imperfections, but rather to mark the maximum stress peak on the colorful picture to assess the outcomes. And I'm like,
Yeah.
okay, that's like, we can do that as well if you like, and we usually add those flags in like PowerPoint or Paint with the numbers. So yeah, this happens too, but I feel that it will be better in time. So that's actually cool. You feel that we've missed anything important about nonlinear FEA?
I mean, it's an endless topic, really. You can never cover
Oh yeah.
all the points, and there's, we didn't really get into any specifics of design. It was all just about the merits of it, I guess. So yeah, I think we've covered a decent amount.
Cool. All right. In that case, Mike, thank you for joining me. It was a huge pleasure to talk with someone from like literally across the world, and that's it's always amazing how those things are becoming easier and easier nowadays. And that's great to share experience. So yeah, thank you for joining. I really appreciate that. Like as Mike nicely said, like I'm starting to have a nonlinear FEA course. If you would be interested, I will like throw a link somewhere below that you can go to the website and see what's going out. Like Mike is already in the course, so I can tell you, Mike, that I just wrote the last lesson. Only the second half of examples is needed. So finally, we're getting there. It was like what, a year and a half already. But it's getting done. So I'm super excited, and you can also expect that there will be quite a lot more nonlinear FEA content that I will produce in coming months. So I'm excited for it as well. So Mike, once more, I really appreciate the time. Thank you so much, and thanks for watching too. See you around.
Cheers.